Yep, it's time for...
What the physics?
Physics.
In this video, we're going to take a look at a Pivot Interactive together. So you can open up Pivot Interactives, do the next one, the bowling ball moving to the right, and you can kind of run this with me. Now everyone's going to get their own trial. We'll talk about that in a little bit. I also walk you through how to write the equation and also how to solve for a prediction. So let's get right to it. Let's go! Deep breaths, remember? Yes. Let's check out something cool. We were looking at Pivot Interactives, and I noticed that we were having some difficulty with figuring out how to do stuff. So I wanted to clarify some of that. So this tutorial is really for those of you who didn't quite get it. So let's dive in. I'm going to do an example here. First things first, as of right now, if you go down and lock your answer and continue, then you get a 0 for those two questions. So you need to make sure you submit your answer, read the comment that's there to help you pick the right one, and make sure you submit it when you do. And you're like, oh, okay, got it, right? And make sure you get the right answers before you lock answer and continue so you can go to the next section and so on. Okay, just wanted to make sure you got that. I'm sorry. In this example that I have here for you, you will be selecting a trial. So the way it works in Pivot is right at the bottom of the video, you'll see a bunch of trials located there. What you need to do is select the one that I assigned to you. I posted a document where you can find that information. All right. And you also notice who else has the same trial as you, along with their email address, so you could maybe hang out with them. Maybe. Collaboration is key when remote learning because you need to bounce ideas off of each other. So collaborate and help each other, but don't cheat. Thanks. Cool. Okay, so let's say I'm going to do, oh gosh, I'm going to did all that and I'm going to go click go and I'm going to do trial 1. And notice I didn't assign anyone else trial 1, so there. Okay, anyway, a couple things. When you are taking data, you will be taking clock readings from the clock that's built in, and you'll be making measurements with the ruler that's built in. Okay, so in this case, we're looking for the bowling ball. So one of the things I want to make sure I do is line up that up really nice. I'm going to move this over and I say, you know what? Let me look at this because last time 0 was not at the beginning. And I noticed the bowling ball does not move until the 3rd frame. So I'm going to click reset on this one here. The clock is at 0 now. So that's good. So we're going to look at that and we're going to start getting data. Now here's the thing. I have my first data point already. I set my 0 point there. So at 0 seconds, it's at 0 centimeters. Wow, it's already done. Now, notice that already my graph has a point. I've already have the origin shown and the linear regression checked. And everything else is already set for me. I can change this if I want to, if I had it backwards or something. But that's it. I had some people adding things here and it was really confusing. So leave those blank. This little box here is the uncertainty box, noted with a plus or minus. That's the give or take. Leave the boxes that are blank, unless I tell you otherwise. Thanks. Okay, so let's fill out 10 data points, and here I go in super fast motion. Okay, so that's how you graph. We have position on the vertical axis and clock reading on the horizontal axis. So its position is increasing in time at a constant rate. If you watch the video, the bowling ball doesn't look like it's slowing down. It looks like it's just going the same pace. Darn bowling balls, always going the same pace. Gah. Henry, I'm looking at you. All right, it says that you need to create an equation.
Pardon me. Don't touch your face! Ah!
If we look back up here, I'm just gonna copy this, paste it right here. Except now I gotta figure out what are the units. Okay, so what the heck are the units there? So position is in centimeters, okay, and the slope is how much the position changes for every clock reading. So how much centimeters for every second. So my first number, that slope there, is centimeters every second. And then it's times clock reading minus the y-intercept. What is on the y-axis? It's centimeters. Now, going to the nearest tenth of a centimeter. So this is the nearest 100th, which pretty much tells me to the nearest 10th centimeter, it should be 0. You know what? It's 0. And I'm going to even make sure you can see to the nearest 10th of a centimeter, it's 0. Okay, so now we're supposed to make a prediction and figure out when will the ball reach that flag. So if we look back, that flag is at, in trial 1, 121.2 maybe? I don't know. My position is 121.2 centimeters. Bam. Okay. What will t equal? So following the same idea, I'm going to show my work on my iPad here. All right, our goal position is 121.2 centimeters. So what would the time be? Based on our model, remember our model's position is equal to 48.5 centimeters per second times time. Well, we plug in position and we solve for t. The units will end up canceling and we end up with seconds. Cool. So that means our time is equal to this number. But where the heck do we round it? Well, good thing they're sig figs. This is 4, this is 3, which means this has to be 3. 2.50 seconds is my answer. So let's figure out the percent difference. We had our prediction and our measurement here. So the percent difference, basically you take the difference of the measured and your prediction, take the absolute value and divide it by the measurement. So let's put in those values and calculate it. Here we go, and divided by that number. Awesome. So that means we get 0.0833 seconds difference, and take the absolute value of that and pretty much ends up being the same thing. Okay, well, we end up with an answer of 0.03224 and so on. But wait a minute, we got to be able to round this somewhere, so there's got to be something we can do about sig figs. Let's go take a look at that subtraction. In subtraction, we have to pay attention to the least precise place, which is this one, which means we have to round this number to the same place, which leaves us with only one sig fig, which means our answer is only going to have one sig fig. That makes it nice. So this means a 3% difference, which means I was 97% sure of my answer. Smiley.
Physics.